Picture this: a star so colossal that if it replaced our Sun, its surface would stretch beyond the orbit of Jupiter. A single heartbeat in its lifetime could outshine entire galaxies. These are not science fiction fantasies, but real cosmic titans lurking in the depths of space, defying everything we thought we knew about the universe. What makes these monstrous stars burn so bright yet vanish so quickly? Why do they hold the keys to the very elements that make up our world? Strap in, because today we're embarking on a journey to unravel 50 mind-blowing facts about the universe's most massive stars. Celestial giants that rewrite the rules of physics, challenge our understanding of time, and sculpt the cosmos with their explosive deaths. From hypergiants that could swallow our solar system whole to mysterious stellar vampires stealing mass from their neighbors, every fact will leave you in awe. By the end of this video, you'll see the night sky not as a static canvas, but as a dynamic, violent, and breathtaking arena where these titans wage their epic battles. Ready to have your mind stretched to cosmic proportions? Let's dive in. Now, let's zoom in on one of these cosmic behemoths, UY Scuti, the largest known star in the universe. Imagine a star so vast that its radius is 1,700 times that of our Sun. To put that into perspective, if UY Scuti were placed at the center of our solar system, its surface would stretch beyond the orbit of Saturn, swallowing everything in its path. This red hypergiant resides in the constellation Scutum, a small but fascinating patch of the night sky. Its sheer size defies comprehension, dwarfing even the most massive objects we're familiar with. But here's the kicker: despite its mind-bending dimensions, UY Scuti isn't the heaviest star out there. Its colossal volume is matched by an equally astonishing fragility, as it sheds enormous amounts of material into space, a reminder that even the universe's biggest giants are fleeting. Just thinking about the scale of this star makes our own Sun seem like a mere speck in comparison, and this is just the beginning. Wait until you hear what comes next. Now let's peel back another layer of these cosmic titans. Hypergiants like UY Scuti don't just sit quietly in space. They're volatile, restless giants, constantly shedding their own mass in violent stellar winds. Picture a star so unstable that it's literally throwing off chunks of itself into the void, losing the equivalent of Earth's mass every single year. This isn't a slow leak, it's a full-blown cosmic tantrum. And here's why that matters. This relentless mass loss is what keeps these stars from growing even larger. The more they expand, the harder it becomes for gravity to hold them together, and the faster they disintegrate. That's also why their lives are shockingly short compared to stars like our Sun. While the Sun will shine steadily for around 10 billion years, hypergiants burn through their fuel in just a few million. Think of it like a fireworks show. The brightest, most spectacular bursts are over in seconds, while a candle flickers for hours. These stars live fast, die young, and leave behind a trail of heavy elements that will one day form new stars, planets, and maybe even life. But their explosive exits aren't just a footnote, they're the universe's way of recycling stardust on a grand scale. And speaking of grand, wait until you hear about the next contender for the title of largest star, Stephenson 218, a cosmic puzzle that's sparking debates among astronomers. Now, let's turn our attention to a star that's stirring up quite the debate in the astronomy community, Stephenson 218. This colossal contender pushes the boundaries of what we thought possible, with some estimates suggesting it dwarfs our Sun by an astonishing 2,150 times. If placed at the center of our solar system, its surface would stretch far beyond the orbit of Saturn, making even UY Scuti look modest by comparison. But here's where things get interesting. Not everyone agrees on whether Stephenson 218 is truly a single star or actually a tight-knit binary system. The uncertainty comes from the challenges of measuring such distant, luminous objects, wrapped in thick clouds of dust that obscure the details. What isn't up for debate, though, is its mind-blowing brightness. Stephenson 218 shines with the luminosity of nearly 500,000 suns, a brilliance so intense it defies comprehension. To put that in perspective, if this star were as close to us as Alpha Centauri, it would outshine the full moon in our night sky. Yet, despite its staggering size and energy output, Stephenson 218 remains shrouded in mystery, a reminder that even the universe's most extreme objects keep secrets waiting to be uncovered. And as astronomers continue to study this cosmic giant, one thing is certain: it challenges our understanding of how massive a star can truly become. Now, let's unravel one of the universe's most fundamental rules, the mass-luminosity relation. This cosmic law reveals a simple but powerful truth: the more massive a star is, the brighter it burns. Take a star just 20 times heavier than our Sun, for example. It doesn't just glow a little brighter, it outshines our Sun by a staggering 10,000 times. That's like comparing a single light bulb to the blazing intensity of an entire stadium's floodlights. But why does this happen? It all comes down to the crushing weight of gravity. A star's immense mass creates such extreme pressure in its core that nuclear fusion kicks into overdrive. More mass means more fuel, but also a far more violent reaction, like pouring gasoline on a campfire. The result, a dazzling, short-lived inferno. This relationship isn't just linear, it's exponential. Double a star's mass and its brightness might skyrocket by 16 times. That's why monsters like Stephenson 218 or R136A1 don't just outshine our Sun, they dominate entire galaxies with their brilliance. Yet, this incredible power comes at a cost. The same physics that makes these stars so luminous also ensures they burn out fast, leaving behind cosmic fireworks that light up the universe in their final moments. Now, let's peel back another layer of cosmic wonder: how these colossal stars manage to hold themselves together against the crushing force of gravity. Picture a star as a cosmic tug of war. On one side, gravity is pulling everything inward, trying to collapse the star under its own weight. On the other side, the radiation pressure from nuclear fusion pushes outward with unimaginable force. This delicate balance is what keeps a massive star from imploding, at least for a while. Deep in the core, hydrogen atoms fuse into helium, releasing energy that radiates outward, counteracting gravity's relentless pull. The more massive the star, the fiercer this battle becomes. In stars like R136A1, fusion doesn't just hum along, it roars like a runaway furnace, generating enough outward pressure to keep gravity at bay. But here's the catch: this balance is temporary. As the star burns through its fuel, the core contracts, heating up even more and triggering heavier elements to fuse. Each new phase buys a little more time, but gravity never stops its siege. Eventually, when the star can no longer sustain fusion, especially once iron starts forming in the core, the scales tip. Radiation pressure falters and gravity wins in a catastrophic instant. But that's a story for another fact, one that involves explosions powerful enough to outshine entire galaxies. For now, just marvel at how these stellar titans walk the tightrope between brilliance and oblivion. Now, let's shift our gaze to the fleeting brilliance of these cosmic giants, because unlike our steady sun, massive stars live fast and die young. Imagine the sun as a marathon runner, pacing itself for 10 billion years, while stars like R136A1 are sprinters, burning through their fuel in just 10 to 20 million years. That's 1,000 times shorter. Why the rush? The more massive a star, the harder its core works to resist gravity, fusing elements at a breakneck pace. It's like pouring gasoline on a fire, spectacular but over in a flash. And here's the cosmic twist: their short lives have a purpose. When these stars finally exhaust their fuel, they don't fade quietly. They explode in supernova, scattering heavy elements like iron, gold, and uranium across space. Every atom in your jewelry, every metal in your phone. they were forged in the violent deaths of stars much larger than our Sun. So while these titans may not stick around long, their legacy is written into the fabric of the universe and even into us. Talk about a stellar retirement plan. Now let's tackle one of the universe's great cosmic rules, the Eddington Limit. This is the theoretical ceiling for how massive a star can get before it starts tearing itself apart, roughly between 150 and 200 times the mass of our Sun. Think of it like a balloon pump in too much air and it pops. Stars face a similar dilemma. Their cores generate so much radiation pressure from nuclear fusion that, beyond this limit, the outward force would overpower gravity, blasting away their outer layers. But here's where things get wild. Stars like R136A1, tipping the scales at over 250 solar masses, seem to laugh in the face of this rule. How astronomers suspect these behemoths might have started even heavier, shedding weight through ferocious stellar winds like a heavyweight boxer sweating off pounds before a fight. Or perhaps they formed through mergers, with two massive stars colliding and combining into one unstoppable titan. Either way, R136A1 and its ilk are rewriting the textbooks, proving that even the universe's rules have their exceptions. And that's what makes studying these cosmic giants so thrilling. They keep us guessing. Now, let's zoom in on the heavyweight champion of the known universe, R136A1. Nestled in the heart of the Tarantula Nebula, a cosmic nursery bursting with young, fiery stars, this colossal beast tips the scales at over 250 times the mass of our Sun. To put that into perspective, if R136A1 replaced our Sun, its sheer gravitational pull would warp the entire solar system beyond recognition. But here's the twist: R136A1 isn't just sitting pretty. It's in a constant battle against its own enormity, shedding mass at an almost unimaginable rate. Picture a cosmic version of a high-speed sandblaster, where violent stellar winds rip away material equivalent to an entire Earth's mass every few months. These winds aren't gentle breezes, they're supersonic tempests, fueled by the star's searing radiation and turbulent magnetic fields. Over time, this relentless weight loss means R136A1 might have started even more massive, perhaps as heavy as 300 solar masses before it began slimming down. What makes this star even more fascinating is its surroundings. The Tarantula Nebula is a star-forming frenzy, a place where stellar titans like R136A1 are born shoulder to shoulder, pushing the limits of what we thought possible. And while R136A1 might eventually lose its crown as the most massive known star, for now, it stands as a dazzling reminder that the universe loves to defy expectations. Now, let's unravel one of the universe's most baffling cosmic deceptions, supernova imposters. These dramatic eruptions fool even seasoned astronomers by mimicking the explosive fury of a supernova, yet the star somehow survives the chaos. Take Eta Carinae, for example. Back in 1843, this hypergiant unleashed a blast so intense it briefly outshone every star in the Milky Way except Sirius. For a moment, it looked like a supernova, but then, against all odds, Eta Carinae held on. What causes these explosive tantrums? Unlike true supernova, where a star's core collapses catastrophically, imposters like Eta Carinae experience violent eruptions triggered by internal instability. Imagine a pressure cooker with no release valve. Radiation builds up until the star's outer layers blow off in a spectacular tantrum, ejecting material equivalent to dozens of suns. These outbursts can last years, shrouding the star in glowing debris that slowly fades, leaving the star wounded but still kicking. Here's the real kicker: supernova imposters might be previews of an even bigger finale. Eta Carinae, for instance, is a ticking time bomb expected to go supernova within the next 100,000 years. Until then, these cosmic fakers keep us guessing, proving that even the mightiest stars have a flair for the dramatic. Now let's journey back to the dawn of the cosmos, where the first generation of stars, known as Population 3 stars, rewrote the rules of stellar size. Unlike today's stars, which are peppered with heavier elements, these ancient giants were made almost entirely of hydrogen and helium, the pristine ingredients of the early universe. This lack of metals, what astronomers call elements heavier than helium, meant they could grow to unimaginable scales, free from the constraints that limit modern stars. Here's why metallicity matters. In today's stars, metals act like a cosmic brake, radiating away heat and preventing gas clouds from collapsing into overly massive objects. But Population 3 stars, with their metal-free composition, faced no such limits. Their gas collapsed effortlessly, birthing behemoths potentially hundreds or even thousands of times more massive than our Sun. Picture a star so colossal it makes UY Scuti look petite, a true titan of the cosmic dark ages. Yet despite their theoretical grandeur, we've never spotted one. These primordial giants lived fast and died young, exploding or collapsing long before telescopes could catch them. Their legacy, though, lingers in the heavy elements they forged, which seeded the universe for future stars and ultimately for us. So while we may never see a Population 3 star directly, their ghostly fingerprints are everywhere, etched into the very fabric of space. Now, let's turn our attention to the cosmic dance of binary star systems, where massive stars don't just grow on their own, they sometimes steal from their neighbors. Take WR20A, for example, a pair of stars each weighing over 80 times the mass of our Sun, locked in a gravitational embrace. These stellar heavyweights don't play nice. In such tight orbits, one star can siphon material straight off its companion, bulking up like a cosmic thief. Here's how it works. When two massive stars orbit closely, the stronger gravity of the more massive one, or the one that expands first, can pull gas straight from its partner's outer layers. This stolen fuel doesn't just vanish, it piles onto the thief, supercharging its growth. Imagine a star feasting on its neighbor's energy, growing even more colossal while its companion shrinks or even gets ripped apart entirely. But this isn't just a one-way street. Sometimes the stolen material forms a swirling disk around the thief, sparking violent outbursts or even triggering supernova prematurely. And in rare cases, both stars can merge, creating a single, monstrous star that defies the usual limits of stellar size. So while these binary systems might seem like celestial drama, they are also cosmic factories, shaping some of the most extreme stars we've ever discovered. Now, let's explore one of the rarest and most dramatic phases in the life of a massive star, the yellow hypergiant stage. Picture a star caught in a cosmic tug-of-war, teetering between expansion and collapse. Rho Cassiopeiae is a perfect example of this unstable brilliance. Unlike the steady glow of most stars, yellow hypergiants swing wildly in temperature, sometimes heating up or cooling down by thousands of degrees in just years. These stars are so massive and unstable that they don't just gently shed material, they violently eject entire layers of their outer atmosphere into space. Imagine a star coughing up chunks of itself in colossal eruptions, each one releasing more energy than our Sun will emit in its entire lifetime. Rho Cassiopeiae did exactly this in 2000, blasting off a shell of gas so vast it dimmed the star's light for years. What makes this phase even more fascinating is how brief it is. Yellow hypergiants spend only a few thousand years in this turbulent state before either collapsing or swelling into something even more extreme. It's like watching a star in its final, desperate act, trying to balance the forces tearing it apart. And when these giants finally go, they don't fade quietly. They leave behind a spectacle that reshapes the cosmos around them. Now, let's shift our focus to a critical cosmic rule that seals the fate of massive stars, the Chandrasekhar limit. This boundary, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, marks the maximum mass a white dwarf star can sustain before gravity overpowers it. For a white dwarf, that limit is about 1.4 times the mass of our Sun. Beyond this point, the star's core can no longer resist collapse, but here's where things get explosive for massive stars. Unlike white dwarfs, which are the quiet remnants of smaller stars, truly massive stars don't stop at the Chandrasekhar limit. Their cores grow so dense and heavy during their lives that they blast right past it. Once nuclear fusion can no longer counterbalance gravity, especially when iron starts piling up in the core, catastrophe strikes. The star has two brutal options: either explode as a supernova, scattering its guts across space, or collapse into a black hole, vanishing from sight entirely. This limit isn't just a number, it's a cosmic checkpoint that dictates how stars die. For smaller stars, it's a peaceful retirement into a white dwarf. For the giants we've been exploring, it's a violent finale that reshapes galaxies. And without this explosive end, the universe would lack the heavy elements that make planets and even life possible. So in a way, the Chandrasekhar limit isn't just about destruction, it's about creation. Now, let's turn our attention to the cosmic divas of the stellar world, luminous blue variables, or LBVs for short. These stars are the ultimate drama queens, prone to wild mood swings that can light up entire galaxies. Imagine a star so unstable it occasionally throws tantrums, ejecting massive amounts of material into space without warning. One of the most famous examples is P Cygni, which put on a spectacular show in the 17th century when it suddenly flared up, becoming one of the brightest stars in the sky, visible even in broad daylight. Astronomers of the time were baffled by its outburst, but today we know this was just P Cygni's way of shedding layers in a violent stellar tantrum. What makes LBVs so unpredictable? Unlike most stars, which burn steadily for billions of years, these blue giants teeter on the edge of instability. Their immense size and luminosity create such intense radiation pressure that their outer layers barely cling on. When the pressure becomes too much, they erupt, shedding colossal amounts of gas and dust in events that can outshine entire star clusters. Some LBVs, like Eta Carinii, have even experienced eruptions so powerful they mimic supernovae, yet somehow the star survives. But don't let their theatrics fool you. These outbursts are more than just cosmic fireworks, they're critical clues about how the most massive stars evolve. Each eruption peels away layers, revealing deeper secrets about the star's core and its eventual fate. And while LBVs might be rare, their explosive behavior leaves an indelible mark on the universe, shaping the chemistry of galaxies and paving the way for new generations of stars. So next time you gaze at the night sky, remember some stars aren't just shining, they're performing. Now, let's venture into one of the most catastrophic fates a star can face, the pair instability supernova. Picture a star so massive, so unstable, that it doesn't just explode, it completely annihilates itself, leaving nothing behind. Stars between 130 and 250 times the mass of our Sun walk this razor's edge. Here's how it happens. Deep in the core of these colossal stars, temperatures and pressures reach unimaginable extremes. Under these conditions, gamma-ray photons, the very energy that helps hold the star up, suddenly transform into something else, pairs of electrons and their antimatter counterparts, positrons. This process, called pair production, steals energy from the core, weakening the radiation pressure that fights against gravity. Without that support, the core collapses inward violently, heating up even further. But here's where things get apocalyptic. The runaway collapse triggers a thermonuclear bomb at the star's heart. Unlike a typical supernova, which leaves behind a neutron star or black hole, a pair instability supernova unleashes so much energy that the entire star is obliterated. No remnant, no second act. The explosion is so powerful it can outshine entire galaxies for weeks, scattering heavy elements like oxygen and silicon across the cosmos in a final, fiery farewell. What's even more fascinating, these events might be rare today, but in the early universe, when the first generation of monster stars roamed, pair instability supernova could have been far more common. They may have even played a key role in seeding the universe with the building blocks for planets and life. So while these stars meet a spectacular end, their destruction lights the way for new beginnings. But before a massive star meets its explosive end, many go through a dramatic final act, the Wolf-Rayet stage. Imagine a star that's been stripped bare, its outer layers violently blown away by relentless stellar winds, leaving its searing hot core exposed to the cosmos. This is the fate of stars like WR102, one of the most extreme examples of a Wolf-Rayet star. These stars are the universe's ultimate revealers. Their furious winds, racing at millions of miles per hour, tear off their own hydrogen envelopes, exposing the heavier elements forged deep inside helium, carbon, even oxygen. It's like watching a cosmic autopsy where the star's inner workings are laid bare before its final collapse. What makes Wolf-Rayet stars so fascinating is their role as supernova precursors. By shedding so much mass, they're essentially prepping their cores for the inevitable. When the end comes, it's often a type IB or IK supernova, a cataclysm that leaves no hydrogen behind, just the raw elements of the star's exposed heart. And here's something mind-blowing. The winds from these stars don't just vanish. They enrich surrounding space with heavy elements, seeding future generations of stars and planets. So while Wolf-Rayet stars might be racing toward their doom, they're also cosmic recyclers, turning their own destruction into the building blocks of new worlds. Now, here's something that might surprise you. When it comes to stars, bigger doesn't always mean hotter. In fact, some of the universe's most massive stars are surprisingly cool compared to their smaller, bluer siblings. Take Betelgeuse, the famous red supergiant in Orion's shoulder. While it's one of the largest known stars with a radius hundreds of times wider than our Sun, its surface temperature is a relatively chilly 3,500 Kelvin. That's less than half the heat of Rigel, the blue supergiant shining at Orion's foot, which burns at a blistering 12,000 Kelvin. So why the difference? It all comes down to size and stage. Red supergiants like Betelgeuse are massive stars in their twilight years, having expanded into bloated, cooler giants as their nuclear fuel dwindles. Their energy spreads across a vast surface area, lowering the temperature. Meanwhile, blue stars like Rigel are younger, hotter, and more compact, packing their energy into a tighter space. But don't let the word cool fool you. These red giants are still unimaginably powerful. Their sheer size means they're incredibly luminous, even if their surface feels cooler to the touch. And here's the kicker. Their lower temperatures actually make them ideal factories for creating cosmic dust, the very stuff that forms planets and even life. So while they might not burn as hot, their role in the universe is anything but cold. Up next, we'll explore how these aging stars defy expectations even further as they evolve along a path astronomers once thought impossible. Now, let's unravel a fascinating twist in the life of massive stars, one that left astronomers scratching their heads for decades. When these cosmic giants age, they don't just fade quietly into the night. Instead, they balloon into red supergiants following a path called the Hayashi track. This phenomenon completely upended early ideas about how stars evolve. Back in the day, scientists assumed stars would simply shrink as they ran out of fuel, growing denser and hotter. But nature had other plans. Massive stars like Betelgeuse defy this logic by expanding dramatically, their outer layers cooling as they stretch into colossal, unstable behemoths. The Hayashi track explains why these stars reach a point where their cores contract while their outer envelopes puff outward, creating a delicate balance between gravity and radiation pressure. What's truly mind-blowing is how this process reshapes our understanding of stellar life cycles. The Hayashi track revealed that stars don't follow a linear path. Instead, they zigzag across temperature and luminosity charts, swelling and shrinking in ways that early theories never predicted. And here's the kicker. Without this expansion, the universe would lack the heavy elements and cosmic dust that red supergiants scatter into space, ingredients essential for new stars, planets, and even life itself. So the next time you gaze at a red supergiant, remember, it's not just a dying star, it's a rebel rewriting the rules of stellar evolution with every fiery breath. But here's something even more astonishing: nature has a built-in safety switch for these colossal stars. Meet the Humphreys-Davidson limit, a cosmic boundary that puts a hard cap on how big a star can grow. Beyond roughly 1,500 times the radius of our Sun, a star simply can't hold itself together. The forces at play become too extreme, causing these giants to shed their outer layers at a staggering rate, like a sandcastle crumbling under its own weight. This limit isn't just a random number, it's a tipping point where radiation pressure overwhelms gravity. Imagine a star so massive that its own light pushes its surface material into space faster than gravity can pull it back. Stars that flirt with this boundary, like the infamous VY Canis Majoris, are essentially living on borrowed time, violently ejecting enough material to form entire planets every few centuries. What's truly fascinating is how this limit shapes the universe's most dramatic stellar stories. Without it, we might see hypergiants swelling to unimaginable sizes, only to vanish in cosmic tantrums. Instead, the Humphreys-Davidson limit ensures these titans meet a more controlled, though still spectacular fate, seeding galaxies with the heavy elements that make life possible. So while these stars may not break the size record, they certainly break the mold, proving even the universe has its limits. Now let's turn our attention to a star that's been quietly fading from its former glory, the Pistol Star. Once a dazzling beacon shining with the brightness of 6 million suns, this hypergiant has dimmed to a mere 1.6 million times our Sun's luminosity. What caused such a dramatic decline? The answer lies in its relentless shedding of mass, a process so intense that the Pistol Star has already ejected material equivalent to several suns. Picture a cosmic heavyweight champion slowly losing its strength over time. The Pistol Star's violent stellar winds have stripped away layers of its outer envelope, like a sculptor chiseling away at a block of marble. This isn't just a slow fade, it's a rapid unraveling, with the star losing enough mass every few thousand years to form an entire solar system. What makes this even more intriguing is the star's location in the quintuplet cluster near the Milky Way's center, where it's surrounded by a glowing nebula of its own discarded material. That nebula, aptly named the Pistol Nebula, serves as a ghostly reminder of the star's past brilliance. While the Pistol Star may no longer be the brightest titan in the galaxy, its story teaches us a crucial lesson. Even the mightiest stars are bound by the relentless laws of physics, destined to fade as they pour their essence back into the cosmos. Now, let's venture into one of the most explosive events in the cosmos, kilinovae, and how these violent collisions might actually give birth to new cosmic giants. When two neutron stars spiral into each other, the resulting kilonova explosion is so powerful it outshines entire galaxies for days. But here's the twist. In the chaotic aftermath, some scientists speculate that under just the right conditions, these mergers could forge something unexpected: ultra-massive stars. Imagine the sheer force of two city-sized neutron stars, each more massive than our Sun, smashing together at nearly the speed of light. The energy released doesn't just scatter heavy elements like gold and platinum across space, it might also trigger the formation of a temporary superheated fireball. In rare cases, this fireball could collapse under its own gravity, igniting a newborn star with a mass hundreds of times greater than our Sun. While we've yet to observe this phenomenon directly, computer simulations suggest it's possible. Picture a cosmic phoenix rising from the ashes of destruction, a star born from the wreckage of a cataclysmic merger. These hypothetical ultra-massive stars would burn furiously and die young, but their existence would rewrite our understanding of stellar origins. It's a reminder that even in the universe's most violent moments, creation and destruction are often two sides of the same coin. So next time you hear about a kilonova, remember, it might not just be the end of two neutron stars. It could also be the dramatic beginning of a stellar titan. Now, let's turn our gaze to one of the most mind-bending ideas in astrophysics, the quasi-star. Picture this, a star so colossal it makes UY Scuti look like a speck powered not by nuclear fusion, but by a black hole at its heart. These theoretical monsters, 1,000 times more massive than today's biggest stars, might have existed only in the universe's chaotic infancy. Here's how it could work. In the early cosmos, clouds of pure hydrogen and helium collapsed under gravity, forming stars of unimaginable size. But unlike modern stars, a quasi-star's core wouldn't ignite fusion. Instead, it would collapse directly into a black hole. Yet the star wouldn't die. The black hole would feast on the surrounding gas, releasing so much energy it would push back against gravity, keeping the star's outer layers intact. Think of it like a cosmic engine, with a black hole acting as the furnace and the star's body as the fuel. These quasi-stars would have been fleeting giants, shining with the brightness of small galaxies before their black hole cores consumed them entirely. Their existence could explain some of the supermassive black holes we see today, those lurking at the centers of galaxies, billions of times heavier than our Sun. If quasi-stars were real, they'd be the ultimate missing link between the first stars and the black holes that now dominate cosmic landscapes. While we've never spotted one, their potential existence challenges everything we know about stellar limits. It's a reminder that the early universe was a laboratory of extremes, where the rules of physics were stretched to their breaking point. So next time you marvel at today's massive stars, remember, they might just be the tame descendants of true cosmic titans. Now, let's uncover a cosmic drama that plays out in the shadows of these stellar giants, the vampire star phenomenon. Imagine a binary system where a smaller, hungrier star orbits a massive hypergiant. Over time, the gravitational pull of the smaller star siphons off material from its larger companion, like a celestial thief stealing gas and dust. This stolen mass doesn't just vanish, it fuels the vampire star, causing it to grow brighter and hotter while the hypergiant slowly withers away. Here's where it gets even more fascinating. The stolen material forms an accretion disk around the vampire star, a swirling vortex of superheated gas that glows intensely as it spirals inward. This process can trigger violent outbursts like stellar flares or even sudden brightness surges, making these systems some of the most unpredictable in the cosmos. Meanwhile, the hypergiant, now stripped of its outer layers, may skip its expected evolutionary stages, rushing toward a supernova or collapsing into a black hole far sooner than it would have alone. But the vampire star's feast isn't endless. As it gorges on its companion, it can reach a point where it can't handle the influx of material, leading to explosive ejections or even a merger. These cosmic encounters rewrite the fates of both stars, creating bizarre hybrids or leaving behind exotic remnants like blue stragglers. Stars that appear unnaturally young because they've stolen a second life from their neighbors. So while hypergiants may dominate the spotlight with their sheer size, it's often their smaller, stealthier companions that pull the strings behind the scenes, proving that even in the vastness of space, no star is truly an island. Now, let's turn our attention to the mesmerizing dance of pulsating stars, where even the mightiest giants aren't immune to cosmic rhythms. Take Mu Cephei, nicknamed the Garnet Star for its deep red glow. This colossal star doesn't just shine steadily. Instead, it breathes, expanding and contracting like a celestial heartbeat. What drives this pulsation? It's all thanks to a region astronomers call the instability strip, a narrow zone in the stellar life cycle where stars become unstable to pressure changes deep within their cores. Here's how it works. As fusion reactions heat the star's interior, radiation pressure builds up, pushing the outer layers outward. but once those layers expand, they cool and lose pressure, causing them to fall back inward under gravity's pull. This cycle repeats every few months or years, making the star rhythmically brighten and dim. Mu Cephei, for instance, swings in brightness by nearly a full magnitude, a change visible even to backyard telescopes. These pulsations aren't just a light show. They reveal secrets about the star's internal structure, like a cosmic sonogram. By studying the timing and intensity of these pulses, astronomers can estimate the star's density, temperature, and even its future fate. Some pulsating hypergiants, like VV Cephei, exhibit such extreme swings that they shed massive amounts of material, speeding their journey toward a supernova. What's truly astonishing is how delicate the balance is. A slight shift in temperature or composition can push a star into or out of the instability strip, turning the pulsations on or off like a stellar switch. So while these stars may seem invincible, their flickering light reminds us that even the universe's titans are governed by invisible, rhythmic forces, a symphony of pressure and gravity written into the fabric of space itself. Now let's zoom in on the final, frantic moments of a massive star's life, a race against time where the universe's heaviest elements are forged in a blaze of glory. Deep in the core, after billions of years of fusing hydrogen and helium, the star enters its endgame, silicon fusion. This isn't a slow burn, it's a cosmic sprint. In less than a day, silicon atoms are crushed together under unimaginable pressure, forming heavier elements like sulfur, argon, and eventually iron. Here's the catch. While earlier fusion stages released energy, iron fusion is a cosmic energy thief. It absorbs energy instead of creating it. This flips the star's fate like a switch. With no outward pressure left to fight gravity, the core collapses in seconds. But before that happens, the outer layers are still fusing lighter elements in concentric shells, like an onion burning from the inside out. At this stage, the star might have a hydrogen-fusing shell, then helium, then carbon, oxygen, and finally silicon, all burning simultaneously around the doomed iron core. The speed of this process is mind-bending. A star like Betelgeuse could spend millions of years as a red supergiant, but its final silicon-to-iron phase lasts less than 24 hours. And here's the twist: the heavier the element, the faster it burns. Carbon might last centuries, oxygen months, but silicon, mere days. This countdown ends with the universe's most spectacular fireworks, a supernova, scattering those freshly forged elements across space. So next time you see iron in your blood or calcium in your bones, remember, those atoms were born in the last, desperate moments of a dying giant, a star that turned its collapse into our creation. But here's something even more astonishing. Before the blinding flash of a supernova lights up the cosmos, the star sends out a ghostly warning. In the final seconds before collapse, trillions upon trillions of neutrinos, tiny, nearly massless particles, blast outward from the dying core. These cosmic messengers travel almost at the speed of light, slipping effortlessly through the star's dense layers like shadows through a wall. This isn't just theory. In 1987, when supernova 1987 exploded in the Large Magellanic Cloud, detectors on Earth picked up a surge of neutrinos hours before the visible light reached us. 24 neutrinos were caught in a matter of seconds, a whisper from a star that had already died 168,000 years earlier. Why does this matter? Neutrinos carry away 99% of the star's dying energy, draining the core like a cosmic battery. Their escape is the final signal that gravity has won and the collapse is unstoppable. Within moments, the shockwave follows, ripping the star apart in a supernova visible across galaxies. So while light grabs our attention, it's the neutrinos that tell the real story first, a silent alarm from the heart of a collapsing giant. And the next time a nearby star dies, these ghostly particles might give astronomers their earliest warning to point their telescopes and witness the end of a cosmic era. Now let's unravel one of the universe's most dramatic cosmic fails, the fallback black hole. Not all supernovae go out with a clean, explosive bang. Some fizzle halfway like a firework that doesn't quite ignite. When a massive star collapses, the outgoing shockwave sometimes loses steam, unable to fully blast the star's outer layers into space. Instead, gravity claws back a portion of that material, dragging it down into the core like a cosmic boomerang. This fallback process creates something bizarre, an overweight black hole, packing more mass than a typical stellar black hole. Imagine a black hole that's had seconds at an all-you-can-eat buffet, gulping down extra gas and dust that should have been scattered across the cosmos. These gluttonous voids can weigh anywhere from 50 to possibly thousands of times the mass of our Sun, defying the usual limits of stellar collapse. Why does this happen? It's all about balance, or the lack of it. If the dying star's core is too dense or its outer layers too clingy, the supernova's explosion falters. The result, a black hole that's not just born from collapse but supercharged by its own unfinished explosion. Astronomers suspect fallback black holes might explain some of the heftier voids we've detected, bridging the gap between puny stellar black holes and the supermassive monsters lurking in galactic centers. So next time you think of a supernova, remember, sometimes death isn't an end, it's a cosmic do-over with gravity writing its own rules. Now, let's turn our attention to another cosmic marvel. The possibility that some massive stars don't just collapse into ordinary neutron stars or black holes but transform into something far more extreme, magnetars. These are neutron stars on steroids, boasting magnetic fields so intense they could strip the data off a credit card from halfway across the solar system. When a massive star dies, its core doesn't always settle for a quiet afterlife as a dense, spinning neutron star. Under the right conditions, like a rapidly rotating core packed with turbulent magnetic fields, the star's collapse might birth a magnetar instead. These objects are rare, making up only about 1 in 10 known neutron stars, but their power is unmatched. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's, capable of bending atoms into needle-like shapes and cracking its own crust in violent starquakes. What's truly mind-blowing is the energy these cosmic powerhouses release. A single flare from a magnetar can outshine the sun for a fraction of a second, unleashing more energy than our star emits in 100,000 years. Some astronomers even suspect that certain mysterious deep space explosions, like soft gamma repeaters, might be magnetars throwing tantrums. Could stars like R136A1 or Eta Carinae end up as magnetars? It's possible if their cores spin fast enough and their magnetic fields are wound up tight during collapse. But here's the catch: magnetars are short-lived by cosmic standards. Their monstrous magnetic fields decay over time, sapping their energy until they fade into quieter neutron stars. So while they might not rule the cosmos forever, for a brief, dazzling moment, they're among the most terrifying and fascinating objects in the universe. Next up, we'll dive into the alchemy of the cosmos, how massive stars forge the elements that make up everything around us, from the gold in your jewelry to the calcium in your bones. Now, let's pull back the curtain on one of the universe's most delicate cosmic recipes, the triple alpha process. This is how massive stars perform their elemental magic, transforming simple helium into the building blocks of life itself. Picture this: deep in a star's scorching core, where temperatures soar above 100 million degrees, helium nuclei, also known as alpha particles, are zipping around at insane speeds. Normally, they'd repel each other thanks to their positive charges, but under these extreme conditions, something extraordinary happens. When two helium nuclei collide, they briefly stick together, forming an unstable beryllium-8 nucleus. Here's the catch: beryllium-8 lasts for just a fraction of a second before it falls apart. But in that fleeting moment, if a third helium nucleus slams into it, the star hits the jackpot. A stable carbon-12 nucleus is born. This three-step fusion dance is so precise it's like threading a needle during an earthquake. The energy conditions have to be just right, too cold, and the helium nuclei won't collide hard enough, too hot, and the beryllium-8 breaks apart before the third helium can join. Why does this matter? Without the triple alpha process, the universe would lack carbon, the backbone of organic molecules. No carbon means no planets, no trees, no you. And here's the kicker, this reaction is incredibly sensitive. Even a 5% change in the strong nuclear force would make carbon production nearly impossible. It's almost as if the universe fine-tuned this process just to make life possible. But the star's work isn't done yet. Once carbon accumulates, it becomes fuel for the next fusion stages, forging heavier elements like oxygen and neon. This is the alchemy that powers the star's brilliance and eventually seeds the cosmos with the ingredients for everything from diamonds to DNA. Up next, we'll explore how this delicate balance can sometimes go catastrophically wrong, triggering explosions that light up the galaxy. Stay tuned. Now, let's turn our attention to a cosmic ticking time bomb, carbon detonation. While we often think of carbon as the quiet backbone of life inside the hearts of massive stars, it can become a volatile fuse waiting to ignite. Picture this: after a star has painstakingly crafted carbon through the triple alpha process, that very same element can spiral into chaos under the right, or rather wrong, conditions. In white dwarfs, the corpses of sun-like stars, carbon detonation is a well-known catastrophe. These dense stellar remnants pack carbon cores under unimaginable pressure. If a white dwarf siphons too much mass from a companion star, crossing a critical threshold, the carbon can suddenly fuse all at once in a runaway thermonuclear explosion. The result, a Type 1, a supernova, one of the brightest fireworks in the universe. But here's where it gets even wilder. Some scientists suspect carbon detonation might not be exclusive to white dwarfs. In the most massive stars, where carbon piles up like dry kindling, a similar chain reaction could theoretically unfold. Imagine a star's core, already a cauldron of nuclear chaos, suddenly triggering a carbon-fueled blast wave. Unlike the steady fusion we've seen so far, this would be a violent, all-or-nothing eruption, potentially shredding the star from the inside out. Why hasn't this been observed yet? For one, the conditions have to be just right or just wrong, depending on your perspective. The star's mass, temperature, and carbon concentration would need to align like a deadly cosmic puzzle. And if it happens, the explosion could rival a supernova, leaving behind a bizarre stellar remnant or nothing at all. This isn't just a stellar curiosity, it's a reminder of how finely balanced the universe's most powerful engines truly are. One misstep in the fusion chain, and a star's life could end not with a slow burn but a spectacular bang. Coming up next, we'll dive into the dazzling yet erratic behavior of stars in their S Doradus phase, where they don't just shine, they put on a full-blown cosmic light show. Stay tuned. Now, let's step into the spotlight of one of the universe's most dramatic performers, the S Doradus phase. Imagine a star so unstable, so wildly unpredictable, that it doesn't just burn bright, it erupts in bursts of brilliance so intense they can outshine entire galaxies. This is the reality for luminous blue variables, or LBV, like the star S Doradus itself. These cosmic divas don't follow the rules. While most stars hum along at a steady brightness, LBVs swing between extremes. In their quiet phases, they might shine with the luminosity of hundreds of thousands of suns, but when they erupt, their brightness can skyrocket to millions or even tens of millions of times the sun's output. For weeks, months, or even years, a single LBV can outglow every star in its host galaxy combined. What fuels these spectacular outbursts? It's a tug-of-war between radiation and gravity. The star's outer layers, already barely held together by gravity, become so hot that radiation pressure overwhelms them. The result, the star violently ejects massive shells of gas like a cosmic souffle exploding out of its pan. These eruptions aren't just bright, they're messy, leaving behind glowing nebulae that tell the story of the star's tantrums. And here's the twist, these outbursts aren't death throes. Unlike supernova, which mark a star's final act, HYPERGIANT-style eruptions are just temporary meltdowns. The star survives, often returning to its normal brightness until the next outburst. It's as if the universe handed these stars a dimmer switch, and they've decided to flick it wildly up and down. But why does this matter? Because LBVs like HYPERGIANT are thought to be a fleeting phase in the lives of the most massive stars, a chaotic prelude to their eventual collapse into black holes or neutron stars. By studying these eruptions, astronomers get a front-row seat to the turbulence that shapes the universe's heaviest hitters. Up next, we'll explore the moment when even the mightiest stars meet their match, the iron core time bomb that triggers their final, catastrophic collapse. Don't go anywhere. Now, let's uncover the brutal truth behind what finally brings even the mightiest stars to their knees, the iron core time bomb. Deep inside a massive star, after millions of years of fusing lighter elements like hydrogen and helium, the core becomes a forge for heavier metals. But when iron starts piling up, disaster strikes. Unlike previous fusion stages, iron doesn't release energy, it steals it. Every time an iron atom forms, it sucks energy out of the core like a cosmic vampire, leaving the star's heart colder and weaker by the second. This is the universe's ultimate betrayal. For eons, radiation pressure from fusion has fought gravity to a standstill, keeping the star inflated. But iron fusion tips the scales. In less than a second, the core's support system vanishes. Without outward pressure, gravity wins catastrophically. The core collapses at nearly a quarter the speed of light, cramming an object heavier than the sun into a sphere just a dozen miles wide. The shockwave from this collapse rips outward, blasting the star's outer layers into space with the energy of a billion suns. This is the supernova we see, a stellar explosion so bright it can outshine entire galaxies. But here's the twist, the real violence happens invisibly. As the core implodes, protons and electrons merge into neutrons, releasing a flood of ghostly particles called neutrinos. These neutrinos carry away 99% of the explosion's energy, and their sheer force helps finish shredding the dying star. Why does this matter? Because this iron-triggered apocalypse is why we exist. The shockwaves forge elements heavier than iron, like gold, uranium, and iodine, flinging them into space to eventually become planets, oceans, and even the iron in your blood. Every time a massive star self-destructs, it's literally sowing the seeds for future life. Coming up, we'll dive into an even more extreme fate when stars so massive they might skip the supernova entirely and vanish into the darkness as black holes. Stay tuned. Now, let's explore a phenomenon so extreme it challenges the very laws of physics, the pair creation catastrophe. Inside the most massive stars, where temperatures and pressures reach unimaginable levels, something bizarre happens. Photons, the particles of light that usually zip through space harmlessly, become powerful enough to spawn matter. When these high-energy photons collide inside the star's core, they can spontaneously create pairs of particles, an electron and its antimatter counterpart, a positron. This might sound like science fiction, but it's a real cosmic crisis. Normally, radiation pressure from photons helps hold the star up against gravity's relentless pull. But when photons transform into matter, that pressure vanishes. It's like removing the supports from a collapsing building. The star's core loses its ability to resist gravity's crush. The more pairs that form, the faster the core destabilizes, accelerating the star toward disaster. What makes this even wilder? The newborn particles themselves don't stick around for long. Electrons and positrons almost immediately annihilate each other, converting back into photons. But this back-and-forth chaos drains energy from the core, further weakening the star's defenses. In stars over 130 times the mass of our Sun, this runaway process can trigger a total collapse or even cause the star to tear itself apart in a pair instability supernova, one of the most violent explosions in the universe. So why does this matter? Because these extreme events aren't just destructive, they're creative. The energy and elements forged in these explosions seed the cosmos with the building blocks for new stars, planets, and even life. Up next, we'll witness an even more spectacular in-game hypernovas, the supernovas that might power the universe's most energetic bursts of light. Stay tuned. Now, let's step into the realm of cosmic fireworks so intense, they dwarf even the most violent supernovas. Welcome to the hypernova. Imagine a stellar explosion so powerful, it outshines an entire galaxy for a brief, blinding moment. Hypernovas are the universe's ultimate tantrums, unleashing energies 100 times brighter than a typical supernova. But what makes them truly special? They might be the cosmic engines behind gamma-ray bursts, the most energetic phenomena we've ever detected. Here's how it works. When a hypergiant star, dozens of times more massive than our Sun, reaches the end of its life, it doesn't just collapse. It implodes with such force that the core doesn't just form a neutron star, it likely crushes itself into a black hole in seconds. But the real spectacle happens when the star's outer layers, no longer supported by the core, come crashing down at nearly the speed of light. This creates twin jets of radiation and matter shooting outward like cosmic blowtorches. If one of those jets happens to point toward Earth, we see it as a gamma-ray burst, a flash so intense it can outshine every star in the Milky Way combined. What's wild is that these explosions might be rare, but their impact is anything but subtle. Hypernovas are thought to forge heavy elements like gold and platinum in their aftermath, scattering them across galaxies. They might even sterilize nearby planets with their lethal radiation, while simultaneously seeding the cosmos with the ingredients for new worlds. And here's the kicker, some scientists believe the Ordovician extinction event, one of Earth's worst mass die-offs, could have been triggered by a gamma-ray burst from a hypernova millions of light-years away. So the next time you look up at the night sky, remember, somewhere out there, a star is preparing for a finale so spectacular, it could rewrite the rules of physics. And speaking of rewriting rules, our next stop is even more unpredictable runaway stars, the cosmic speedsters flung across galaxies by hypernova kicks. Stay with us. Now, let's shift our gaze to the cosmic speed demons of the universe, runaway stars. These aren't your average stellar travelers. They're massive stars hurtling through space at mind-bending velocities, some reaching speeds of hundreds of thousands of miles per hour. Take Zeta Ophiuchi, for example, a blue giant racing through interstellar space so fast it's literally plowing through gas and dust, creating a colossal bow shock in its wake like a ship cutting through waves. So how do stars end up as cosmic fugitives? There are two main escape routes. First, a supernova kick. When a star in a binary system goes supernova, the explosion can fling its surviving companion outward with unimaginable force, like a slingshot gone rogue. Second, gravitational chaos. Close encounters in dense star clusters can slingshot stars into the void, ejecting them at speeds that defy gravity's grip. What's fascinating is the aftermath. Runaway stars don't just vanish into the darkness, they leave behind dramatic trails. Zeta Ophiuchi, for instance, glows fiercely in ultraviolet light as its powerful stellar winds collide with interstellar material, creating a shockwave visible to telescopes. These stars also act as cosmic polluters, spreading heavy elements forged in their cores across vast distances, enriching the galaxy one high-speed journey at a time. But here's the real kicker. Some runaway stars might even be hypervelocity stars, ejected so forcefully they could eventually escape the Milky Way entirely. Imagine a star so fast it's on a one-way trip into intergalactic space. And speaking of interstellar journeys, our next stop takes us to another stellar mystery, why some massive stars suddenly heat up in their final moments, defying expectations. Stay tuned. Now, let's unravel one of the most puzzling twists in stellar evolution, the mysterious blue loops. Just when astronomers think they've figured out how massive stars age, these cosmic giants throw a curveball. Picture this: a star spends millions of years as a red supergiant, swollen and cool, only to suddenly shrink, heat up, and turn blue again in its final act. It's like watching a candle flare brightly one last time before burning out. So why does this happen? The secret lies in the star's internal chemistry. As a massive star nears the end of its life, it begins fusing heavier elements in layered shells around its core. When helium ignites in a shell outside the core, the sudden burst of energy can cause the star's outer layers to contract, heating up its surface. This temporary blue loop phase sees the star shedding its red supergiant cloak and transforming back into a hotter, bluer object, sometimes even becoming a blue supergiant for a brief cosmic moment. But here's the kicker: this phase is fleeting. The star's core continues to churn out heavier elements, and soon the balance tips again. The outer layers re-expand, cooling back into a red supergiant, a final, dramatic swan song before the star explodes as a supernova or collapses into a black hole. What makes blue loops so fascinating is how they challenge our understanding of stellar life cycles. They remind us that even in death, massive stars refuse to follow a simple script. And speaking of final acts, our next stop takes us deeper into the star's core, where elements like silicon and iron mark the point of no return. Stay tuned. Now, let's peel back the layers of these stellar giants to uncover the fiery engine at their core. Imagine a cosmic onion where each layer burns with a different element, powering the star's final furious dance. Deep inside a massive star, fusion isn't just happening at the center. It's a cascading fireworks display with shells of nuclear reactions stacked like nesting dolls. The outermost shell fuses hydrogen into helium, just like in younger stars. But as you dive deeper, things get more extreme. Beneath that, a helium-burning shell transforms helium into carbon and oxygen. Further in, carbon fuses into neon and magnesium, while closer to the core, oxygen burns into silicon. At the very heart of this inferno, silicon is forged into iron, the star's death knell. Each shell ignites only when the temperature and pressure reach a critical threshold, creating a chain reaction that keeps the star balanced against gravity's relentless pull. What's truly mind-blowing is the timescale. While hydrogen fusion can last millions of years, the inner shells work at breakneck speed. Silicon fusion, for example, might last just a single day before the core collapses. This layered burning is why massive stars are such efficient cosmic factories, churning out the elements that will one day form planets and even life. But this delicate balance can't last forever. Up next, we'll explore how these layered fires lead to one of the universe's most violent finales, the supernova explosion. Now, let's shift our gaze from the explosive ends of these colossal stars to the ripples they leave behind in the fabric of space-time. When massive stars meet their fiery demise, they don't just vanish, they often leave behind black holes or neutron stars. And when these remnants collide, they send out gravitational waves, cosmic tremors that warp the very structure of the universe. The groundbreaking detection of these waves by LIGO, the Laser Interferometer Gravitational Wave Observatory, opened a new window into the cosmos. Imagine two black holes, each born from the collapse of a massive star, spiraling toward each other in a deadly dance. As they merge, they unleash energy equivalent to several suns converted into pure gravitational waves, distorting space-time like a stone dropped into a pond. What's astonishing is how these detections confirm the violent legacy of massive stars. The first observed merger in 2015, dubbed GW151226, involved two black holes roughly 30 times the mass of our Sun, likely the remnants of stars that lived fast and died young. These events don't just reveal the afterlife of massive stars, they also help scientists test Einstein's theory of relativity with unprecedented precision. Gravitational waves are more than just cosmic echoes, they're a direct line to the universe's most cataclysmic events. Next, we'll delve into how these stellar titans might even hold clues to one of astronomy's greatest mysteries, dark matter. But what if the universe's most massive stars aren't just hiding in plain sight? What if they're invisible? This brings us to one of astronomy's most tantalizing what-ifs. Could dark matter, the mysterious substance making up most of the universe's mass, somehow fuel unseen supermassive stars? Dark matter doesn't interact with light, making it utterly invisible to telescopes. Yet its gravitational pull shapes galaxies and galaxy clusters. Some theories suggest that in the early universe, dense pockets of dark matter might have collapsed under their own gravity, forming exotic objects called dark stars. Unlike regular stars, which shine by fusing hydrogen, these hypothetical giants could have been powered by dark matter annihilation, a process where dark matter particles collide and release energy. Imagine a star not of fire but of shadow, glowing faintly with the heat of particles we can't see. These dark stars, if they existed, could have grown hundreds of times more massive than even UY Scuti, fueled by an endless supply of dark matter. While no such stars have been detected yet, their remnants might still lurk in the cosmos, disguised as black holes or hiding in the hearts of galaxies. The idea blurs the line between known physics and wild speculation, but that's the thrill of astronomy. Sometimes the universe's biggest mysteries demand the boldest questions. Next, we'll scale things down to a more familiar setting. Just how far would a star like VY Canis Majoris stretch in our own solar system? Now let's bring this cosmic scale down to a perspective we can all grasp. Picture our familiar solar system with the sun at its center, a comforting, steady presence. But what if we swapped it out for one of the universe's true titans like VY Canis Majoris? This red hypergiant is so colossal that if it took the sun's place, its surface would stretch all the way out to Jupiter's orbit. That means Mercury, Venus, Earth, Mars, and even the asteroid belt would be completely engulfed inside this star's fiery atmosphere. To put it another way, light takes about 8 minutes to travel from the sun to Earth. But if VY Canis Majoris sat in our solar system, light would need over an hour just to cross from its center to its outer edge. And Jupiter, normally 5 times farther from the sun than Earth, would suddenly find itself skimming the star's turbulent surface, bathed in unimaginable heat. This comparison isn't just about size, it's about the sheer violence of these stellar giants. Unlike our stable sun, VY Canis Majoris is a turbulent beast, shedding massive amounts of material in violent eruptions. If it were in our solar system, those eruptions would blast planets with radiation and stellar winds powerful enough to strip away atmospheres. Yet even this staggering scale might not be the limit. Some stars, like Stephenson 218, could stretch even farther, perhaps beyond Saturn's orbit. But that's a story for another fact. For now, let's turn our attention to the eerie beauty of a dying hypergiant's final act as it cloaks itself in a shroud of dust and gas. Now let's peer into the dramatic final act of these colossal stars. As hypergiants like IRC plus 10420 near the end of their lives, they don't fade quietly. They go out in a blaze of cosmic spectacle. Imagine a star so massive that it can no longer hold itself together, violently shedding layers of gas and dust in a desperate struggle against gravity. This expelled material forms what astronomers call a dusty death shroud, a thick veil that slowly engulfs the star, hiding it from view like a celestial funeral veil. IRC plus 10420, for instance, is a hypergiant in the midst of this very process. It's ejecting material at a staggering rate, enough to build several Earths every year. Over time, these expelled layers create a glowing nebula around the star, illuminated by its fading but still intense light. The result is a breathtaking but eerie sight, as the star's own outbursts bury it alive in its own debris. What makes this even more fascinating is how these shrouds act as cosmic recycling centers. The gas and dust expelled by dying hypergiants are rich in heavy elements like carbon, oxygen, and even gold, ingredients forged in the star's core during its final, violent phases. When the star eventually explodes as a supernova, this material will be scattered across space, seeding future generations of stars, planets, and perhaps even life. So while the dusty death shroud marks the end for the star, it's also the beginning of something new. And speaking of endings that spark new beginnings, let's turn our attention to an even bigger cosmic mystery: how these massive stars might actually shape the very zones where life could arise. Now, let's explore a cosmic paradox: how the very stars that could snuff out life might also be the reason it exists. Massive stars flood their surroundings with intense ultraviolet radiation, powerful enough to strip away atmospheres and sterilize any nearby planets. Imagine a world bathed in such harsh light. It's a place where life as we know it would struggle to survive, but here's the twist. When these colossal stars finally explode as supernova, they scatter something precious into space, the heavy elements forged in their cores. Carbon, nitrogen, oxygen, even the iron in your blood, all were created in the hearts of massive stars and hurled across the cosmos by their violent deaths. These elements become the building blocks for new stars, planets, and ultimately, life itself. Take our own solar system as an example. The iron in Earth's core, the calcium in your bones, and the oxygen you breathe, all were likely forged in a massive star that died billions of years ago. Without these stellar furnaces, the chemistry of life simply wouldn't exist. So while a hypergiant's radiation might render its immediate neighborhood uninhabitable, its legacy enriches the wider galaxy, creating the conditions for life to emerge elsewhere. It's a delicate balance: too close to a massive star and a planet is cooked by radiation; too far and it might lack the essential ingredients for life. But somewhere in between lies the cosmic sweet spot, where the ashes of dead stars give rise to new possibilities. And that brings us to our next revelation: how these titans don't just shape individual worlds but entire galaxies. Now let's shift our gaze to a phenomenon that turns these stellar titans into cosmic recyclers: the galactic fountain effect. Picture this: when a hypergiant star reaches the end of its life, it doesn't just vanish quietly. Instead, it unleashes furious stellar winds or explodes in a supernova, ejecting vast amounts of gas and heavy elements into space at staggering speeds. This material doesn't just linger nearby, it gets flung far and wide, soaring through the galaxy like a celestial geyser. These ejected elements, oxygen, silicon, iron, and more, mix with cooler interstellar gas, creating dense clouds that eventually collapse to form new stars and planets. It's a cycle as old as the universe itself. Stars die, scattering their remains, and those remains birth the next generation. In spiral galaxies like our Milky Way, this process creates towering fountains of gas, where material is blasted upward from the galactic disk, only to rain back down later, enriching entire regions with the ingredients for future solar systems. What's truly remarkable is the scale. A single hypergiant's death can seed thousands of light years with fresh material, ensuring that no corner of a galaxy remains untouched by its legacy. Without this recycling program, galaxies would eventually run out of the raw materials needed to form stars, planets, and even life. So the next time you look up at the night sky, remember, those twinkling lights aren't just stars. They're part of an endless cosmic dance, fueled by the explosions of giants long gone. And speaking of explosions, let's turn our attention to another mystery: why some of the universe's most massive red supergiants seem to vanish without a trace. But here's a puzzle that has astronomers scratching their heads: where are all the heavyweight red supergiants? You'd expect stars above 25 times the mass of our Sun to swell into these colossal, crimson orbs as they age, just like Betelgeuse. Yet, strangely, we've spotted very few red supergiants in this weight class. It's as if the universe has a missing persons case on its hands, One theory suggests these massive stars might skip the red supergiant phase entirely. Instead of cooling and expanding, they could stay hot and blue, burning through their fuel so violently that they collapse straight into supernova or even black holes without ever turning red. Another idea is that their outer layers get shredded by powerful stellar winds before they have a chance to puff up, leaving behind exposed cores that masquerade as different types of stars. Then there's the observational challenge. Red supergiants are notoriously unpredictable. Some might dim dramatically due to dust clouds, making them harder to spot, while others could evolve so quickly that their red supergiant phase is over in a cosmic blink. It's a reminder that even the most massive stars in the universe still keep a few secrets tucked away. And speaking of secrets, let's unravel another enigma. What happens when a neutron star gets trapped inside a red supergiant? That's a cosmic oddity you won't want to miss. Now, let's dive into one of the most bizarre cosmic what-ifs, the Thorne-Zitkow object. Picture this: a neutron star, the dense corpse of a dead star, somehow gets swallowed up by a red supergiant. Instead of being torn apart, it survives, orbiting deep inside the giant's belly like a stellar parasite. This strange pairing would create a star within a star, a cosmic Russian doll that defies everything we know about stellar evolution. The idea was first proposed in the 1970s by physicists Kip Thorne and Anna Zitkow, who calculated that under the right conditions, a neutron star could spiral into a red supergiant's core without triggering an immediate catastrophe. The neutron star's gravity would stir up the supergiant's insides, altering how it burns fuel and possibly even producing unusual elements like rubidium and lithium in its outer layers. But here's the catch: no one has ever confirmed a Thorne-Zitkow object exists. A few candidates, like HV 2116 in the Small Magellanic Cloud, have shown odd chemical signatures that hint at this hybrid nature, but proof remains elusive. Some astronomers argue these stars might be masquerading as something else, or perhaps the conditions to form them are so rare that we've simply not spotted one yet. If they do exist, Thorne-Zitkow objects could rewrite the rules of stellar life and death. Imagine a star that doesn't die with a supernova, but instead gets consumed from the inside out, its core replaced by a ticking time bomb of ultra-dense matter. It's a reminder that even the wildest theories in astrophysics might be hiding in plain sight. We just need to know where to look. And speaking of stellar oddities, let's shift our gaze to another cosmic mystery: the way light from dying stars can echo across space, revealing secrets long after the star itself is gone. Now, let's turn our attention to one of the most mesmerizing tricks of the cosmos, the light echo. Imagine a star erupting in a violent outburst, sending a brilliant flash of light racing through space. But here's the twist: that light doesn't just vanish. Instead, it bounces off surrounding clouds of dust, creating a delayed glow that can linger for years, like a cosmic ripple in a pond. Take V838 Monocerotes, for example. In 2002, this enigmatic star suddenly flared up, becoming 600,000 times brighter than our Sun. But the real magic happened afterward. As the initial burst of light traveled outward, it illuminated shells of dust that had been ejected by the star centuries earlier. Over the next several years, telescopes captured these expanding rings of light, a stunning visual echo of the original explosion. Light echoes aren't just pretty to look at, they're cosmic time machines. By studying how the light interacts with the dust, astronomers can map the star's past eruptions and even calculate the structure of the surrounding space. It's like peeling back layers of an onion, revealing secrets about the star's history that would otherwise be lost to time. And while V838 Monocerotes is the most famous example, light echoes have been spotted around other massive stars too. Each one tells a story of chaos and beauty, a fleeting moment of stellar drama frozen in the glow of scattered light. Up next, we'll explore how these celestial giants play a surprising role in helping us measure the vast distances of the universe. Now, let's uncover how these colossal stars act as cosmic yardsticks, helping us map the unimaginable vastness of the universe. Enter Cepheid Variable's massive pulsating stars that serve as one of astronomy's most reliable distance markers. These stars have a unique superpower. Their brightness fluctuates in a predictable rhythm, and the rate of their pulsations is directly tied to their true luminosity. Here's why that matters. Imagine you're standing on a dark road watching two identical lanterns, one close by and one far away. The farther lantern appears dimmer, but if you know both emit the same amount of light, you can calculate the distance to the more distant one just by comparing their brightness. Cepheid variables work the same way. By measuring how quickly they pulse and how dim they appear from Earth, astronomers can determine their true distance with remarkable precision. This method, known as the cosmic distance ladder, has been pivotal in measuring everything from nearby galaxies to the far edges of the observable universe. In the early 20th century, Edwin Hubble used Cepheids to prove that the Andromeda galaxy lay far beyond our Milky Way, revolutionizing our understanding of the cosmos. Today, they remain essential tools, helping us calibrate other distance measuring techniques and even refine calculations about the universe's expansion rate. What's truly mind-blowing is that these pulsating giants bridge the gap between local and distant cosmic landmarks, stitching together a coherent map of space itself. Without them, we'd be stumbling in the dark, unable to grasp the true scale of the universe we call home. Coming up, we'll delve into an even more mysterious fate awaiting some massive stars, a collapse so silent it defies expectations. Now, let's explore one of the most puzzling cosmic vanishing acts, the failed supernova. While we often picture massive stars going out with a spectacular bang, some might disappear without a trace. Imagine a star so massive that instead of exploding, it simply implodes, vanishing straight into a black hole. No blinding flash, no shockwave, just silence. This eerie scenario happens when a star's core collapses under its own gravity so abruptly that the outer layers don't have time to rebound and explode. Instead, they're swallowed whole like a cosmic magician's trick. Astronomers have even caught hints of this phenomenon: stars that were there one moment and gone the next, leaving behind only an invisible black hole. What makes this even stranger is that these silent collapses challenge our understanding of stellar deaths. Supernovas are supposed to scatter heavy elements across space, but failed supernovas might lock them away forever. Could this explain why we've observed fewer supernovas than expected from the universe's largest stars? The mystery remains unsolved, but one thing's certain: the cosmos still has plenty of surprises up its sleeve. Next, we'll tackle another cosmic curveball: how hypergiant dimming has fooled even scientists into suspecting alien megastructures. Now, let's unravel a cosmic case of mistaken identity, the so-called alien megastructure mystery. Back in 2015, astronomers noticed something bizarre about a star called KIC 8462852, better known as Tabby's star. Its light dimmed erratically, sometimes dropping by a staggering 22%. For context, even a giant planet like Jupiter would only block about 1% of a star's light. This bizarre behavior sparked wild theories, including the idea that an advanced alien civilization had built a massive structure, like a Dyson swarm, around the star to harvest its energy. But before we start drafting first contact protocols, let's look at the real culprit: hypergiant stars. Stars like Tabby's often undergo dramatic dimming due to colossal clouds of dust ejected from their surfaces. These dust clouds, sometimes larger than our entire solar system, orbit the star in irregular patterns, blocking its light in unpredictable ways. What's fascinating is how this natural phenomenon perfectly mimics the hypothetical signature of an artificial megastructure. It's a reminder that the universe often has simpler, if no less spectacular, explanations for its oddities. While the alien megastructure theory captured imaginations, the truth lies in the turbulent lives of hypergiants, stars so massive they shed entire worlds' worth of material into space. So next time you hear about a star acting strangely, remember, it's probably just cosmic drama, not extraterrestrial engineering. And speaking of drama, our final fact takes us to the future of the universe's mightiest stars and why their golden age might already be over. Now let's peer into the cosmic crystal ball and ask a startling question. Will there ever be another star as colossal as UY Scuti? The answer lies in a silent shift happening across the universe. As galaxies age, their metallicity, the abundance of elements heavier than hydrogen and helium, slowly declines, and that's a problem for future giant stars. You see, metals, in astronomical terms, act like a stellar coolant. They help massive stars radiate heat more efficiently, allowing them to grow without tearing themselves apart. Early in the universe, when metals were scarce, stars could theoretically balloon to hundreds or even thousands of times the sun's mass. But today, as galaxies become more metal-rich, stars face a ceiling. The extra metals make their outer layers too opaque, causing intense radiation pressure that blows away excess material before the star can grow to hypergiant proportions. This means the era of true cosmic titans might already be behind us. Future stars, even in metal-poor dwarf galaxies, will struggle to reach the staggering scales of UY Scuti or Stephenson 218. Instead, the universe may become a place of smaller, hotter stars, brilliant but no longer behemoths. Yet there's a poetic twist. The very metals limiting future giants were forged in the deaths of their ancestors. Every atom of oxygen in your lungs, every speck of iron in your blood, was once part of a star that lived fast, died young, and littered the cosmos with the ingredients for new worlds and life itself. So while the age of hypergiants may fade, their legacy is written in the stars and in us. And with that, we've reached the end of our journey through 50 mind-bending facts about the universe's most massive stars. If this cosmic tour left you starstruck, smash that like button, subscribe for more deep space mysteries, and let us know in the comments which fact blew your mind the most. Until next time, keep looking up. As we wrap up this cosmic journey through the universe's most massive stars, let's take a moment to reflect on the incredible scale and drama of these celestial titans. From UY Scuti's mind-bending size to R136, A1's staggering mass, from the explosive tantrums of luminous blue variables to the quiet fade of hypergiants like the Pistol Star, we've explored 50 astonishing facts that reveal just how dynamic and violent the lives of these stars truly are. But here's the most humbling thought of all: every one of us is connected to these distant giants in the most intimate way. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in the hearts of massive stars and scattered across the cosmos when they died in spectacular supernova. In the grandest sense, we are all made of star stuff, carrying the echoes of these cosmic furnaces within us. So the next time you gaze up at the night sky, remember, those twinkling lights aren't just distant suns. They're the architects of existence itself, the factories that built the very elements of life. And while the era of hypergiants may be fading, their legacy lives on in the planets, the stars, and in you. If this journey through the universe's most massive stars left you awestruck, don't keep it to yourself. Drop a comment below and tell us which fact blew your mind the most. Was it the sheer size of Stephenson 218, the violent winds of Wolf-Rayet stars, or the mind-bending idea of quasi-stars powered by black holes? Let's keep the conversation stellar, and if you're hungry for more cosmic mysteries, hit that subscribe button and ring the notification bell so you never miss a voyage into the wonders of space. Until next time, keep exploring, keep wondering, and never stop looking up. The universe has so much more to show us.